recording. So let me do that and let me adjust this. And again, as per our announcement, I will hold a study session during our normal class time on Monday, even though we won't have class, because we aren't supposed to have classes during that time. Again, the study session is completely non-mandatory. I am doing it so that you can really see what you've learned and also make sure that you're prepared for the final exam. Okay, I'm not going to tell you what's on it because I can't, but I can tell, but you can kind of tell like the things I'm interested in. I like, speaking of things I'm interested in, I love this problem, the collat sequence. All right, so it's an iterative sequence where you've got a set of positive integers, and what you do is you create a chain. If you're at n, if n is even, your next number is n divided by 2. If your number is odd, you multiply n by 3 and add 1. So for instance, if we start with 13 is odd, so we multiply 13 by 3, which gives us 39, add 1. That gives us 40. Now 40 is even, so divide by 2. 20 is even, so divide by 2. 10 is even, so divide by 2. We get 5. 5 times 3 is 15, plus 1 gives us 16, right? So whenever something's odd, we multiply by 3, add 1. Divide by 2, divide by 2, divide by 2, divide by 2. And once you get to 1, right, you kind of get into a loop because because 4 would go to 1 would go to 4, 4 would go to 2, 2 would go to 1, and so on and so forth. So we simply say if we get to 1, we're done. Now here's the thing. It can be seen that this sequence, right, has 10 terms. Although it's not yet been proven, the collat problem, it is thought that all numbers start and finish at 1. So in other words, the collat's conjecture is, given these rules, any positive integer n will eventually end up at 1. This is an unproven problem in mathematics, and I believe there is a standing $50 bet on it. So, so not as much as NP Complete, which has got $1 million prize on it, but you'd be just as famous. Is an unsolved problem. Sorry, $500. So there you go. It is complete. It is an extraordinarily difficult problem, completely out of reach of present-day mathematics. So if you want to waste a day thinking about it, I would do that. Anyway, it's a fun problem, but a lot of these problems can't be solved by hand. They're math problems that can't be solved by hand. Your homework, however, is an exception. It's one of these. It is passcode derivation. And this one you can solve by hand, although we're not going to. Okay, so password derivation. This is your homework. A common security method is for online banking. They say it's common, but I've never heard of it, is to ask the user for 3 random characters from the passcode. So for instance, if the passcode was 531278, if that was your passcode, they might ask you for the second character, the third character, and the 5th character. And so then you would type in 317 because the second character would be 3, the first character would be 1, and the second and the 5th character would be 7. So now this isn't completely clear here, but here's a text file, which is, we assume that maybe we've exfiltrated this text file somehow. And it's got a bunch of 50 successful login attempts. Now I should mention, because this doesn't, that these are the same login attempts from the same password. Okay? Given that the 3 characters are always asked for in order, analyze the file so as to determine the shortest possible secret passcode of unknown length. So what that means is that basically, so let's analyze that. 3 characters are always asked for in order. So we'll always ask for the second character, the third character, and the 5th character, but never the third, the second, and the 5th, never the 5th, the second, and the third, right? It's always got to be second, third, 5th. In other words, let's look at these things. So if we look at this 319 over here, we know 2 facts about this already. Okay, we know that a 3 is in the password, a 1 is in the password, and a 9 is in the password. But also, because of given the characters are always asked for in order, and thus they are always entered in order because these are successful login attempts, that means that we know that the 3 comes in the password, comes before the 1 in the password, comes before the 9 in the password. Following me so far? Okay, promise, it's not that bad. Analyze the shortest, the file is to determine the shortest possible secret passcode of unknown length. Well, the shortest possible thing would mean that there's no repeats. Okay, if there were repeated numbers, we would not, and you'll see my answer, which you can use to check your answer. There's not any. So this is a security problem, right? But it's not. It's actually just a graph problem dressed up as a security problem. This is a thing we call topological sorting, which is a different type of sorting algorithm we've seen before. Topological sorting is done when you're dealing with like installing packages or like installing things from GitHub. Basically, it's asking, hey, you know, when you download a program sometime, or like even a video game, it says, hey, in order to run your video game, we need to download these packages first, right? Well, how do you, and sometimes those packages are required to install other additional packages. The way that kind of is figured out is by topological sorting. Same kind of idea here for figuring out what classes you can register for. That's just a topological sort. If you've to figure out what order you need to take your classes in. Basically, anything where we're looking at requirements, that's a topological sort. But also, and so how does this go into a graph? Well, graphs, again, are all about relationships. You know, we need to, if you really want to get a good grasp of that, a good grasp of graphs, okay, then you want to look at, then you want to kind of move away from like what the traditional texts say, which is like all the examples are always about cost or maps, which are very intuitive. Don't get me wrong, those are intuitive. But in the day of social media, that is not the most intuitive example, believe it or not. And it really limits you to thinking, okay, it's like we're looking at maps and, you know, flows and stuff. It's all about relationships. And if you want to translate random data into a graph, you got to ask yourself, what is the data and what is the relationship between the data, right? What do I mean by social networks? Again, just like my example in class, right? Look at like Facebook, because that's pretty simple. If you're friends with somebody, then so Facebook is just a giant graph. Every person on Facebook is a node, and and if you're a friend with person, then a friend with a person, you've got an undirected edge between them. Basically what it gets down to. So here, let's look at these numbers. So how do we translate this into a graph? Well, we know there's a 3, there's a 1 in the graph, and a 9 in the graph. And these are our nodes, because that's the data. The data is the nodes. The edges are the relationship between the data. So what is the relationship between the 3, the 1, and the 9? The 3 comes before the 1, and the 1 comes before the 9. Also, technically, yes, we could say the 3 comes before the 9, but we don't really need to put that in, okay? Okay, don't necessarily need to make that logical loop, because we kind of get that implied by the 3 going to the 1 going to the 9. So we have a directed edge where we get from 3 to 1 and 1 to 9. So let's put in the next one, 6, 8, 0. Okay, so we have a 6 comes before an 8, which comes before 0 in the password. Now we read this and we see 1, 8, 0. So we know that a 1 comes before an 8 and that comes before 0. That's already in there. Don't need to put that in there. All right, now we've got 6, 9, 0. So let's go ahead and toss it there. So we've got a 6 coming before a 9, and the 9 comes before 0. That's another point of data that's pretty useful there. Okay, 1 comes before 2, which comes before 9. So we're going to just slap this 2 up there. 1 comes before 2, which comes before 9. Now, what did I mean by no repeats? Well, if it's got no repeats here, then we're not going to basically say 9 goes to 1, which can then go to 3 and stuff like that. What we're going to end up with is a special type of graph. A DAG. a directed acyclic graph. And that looks, I'm sure, especially intimidating to you if English is not your first language. So let's just take that acronym apart. Directed. The D is for directed. What does directed mean? Well, we know what a graph is. That's one part already down. So directed acyclic graph, that's a type of graph. Directed acyclic graph. Directed means that it's got directed edges. Boom, we know what directed edges are. So acyclic. Okay, weird word, and honestly never came up before I learned directed acyclic graph. Well, just some weird English analysis here. What? Acyclic, as in we're dealing with cycles. Okay. English is a terrible language. We basically just went over to all the other languages and mugged them for all their words. Okay. So cyclic means that we are dealing with cycles. And A, before anything, acyclic in this context means no cycles. So acyclic means no cycles, so directed acyclic graph. This is a directed graph without any cycles. And if we watch this, right, if we choose any point in the graph and we go along an edge, we're not going to get back to anywhere we started, right? We're always going to go and end up at some end location. Okay, so that was 1, 9, 2. So let's look at, we've got also 6, 2, and then 2 goes to 0. It's a bit messy. That's okay. Your computer's better at doing this. This is so I have my doubts as to whether this graph is planar. So that's another term for graphs that you don't necessarily need to know for your final exam or anything. It's just kind of a term that's useful to introduce here. There's a nice complicated definition for planar graphs, which I will pull up now. And yes, I know it's impossible to see, right? Blah, 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 blah. Euler's formula for a planar graph is V minus E plus F is equal to 2. It's actually pretty useful. Again, I've got a video. I've got this awesome playlist, by the way, called Videos Worth Watching, which has a puzzle that relies off of planar graphs. But what does a planar graph mean with all that? It means that for a planar graph means it can be embedded in a plane. What the heck does that mean? That means a graph is planar if I can draw the nodes and the edges such that the edges will not there's not going to be any overlap with the edges. So over here, so this guy, over here, this is what makes it not planar. Now maybe I could draw it in some way that would make it planar, but I don't know. So it's just one of those interesting things about graphs. Graphs are really awesome. Because people have studied them forever and there's all these useful properties. So let's see. Now let's get 7, 6, 2. We already have that. 6, 8 to 9. 7, 6, 2 again. We have that. So there's going to be repeats in your input file. 3, 1, 3, 1, 8, 3, 6, 8, 7, 1, and then 1 goes to 0. It's still directed acyclic, trust me. 7, 2, 0. Okay, I think I can stop here with this horrible amalgamation. So this looks horribly complicated, right? Got arrows everywhere. It doesn't help that I suck at drawing, right? So how in the world are we supposed to sort this, right? How do you do a topological sorting to figure out what needs to be pressed first? Well, we've got an algorithm here called Kahn's algorithm. You know, just you can remember the spelling like from Star Trek, Kahn, that kind of thing. But Kahn's algorithm is an algorithm I think from the 50s, and I'm going to you can look it up on Wikipedia. I highly recommend you use this to program your solution, but it's super simple to explain on paper. What we do is we look, oh, hold on. I need to do one thing first. I need to scroll down because I just realized I'm going to break my algorithm unless I have here we go. Okay. I know what I need. So we have 736 as well. So I'm going to put that in 736. Okay. So what does Kahn's algorithm do? Kahn's algorithm says the topological sorting of something relies off of what we call a property called a node's in-degree. What in the world is an in-degree? The in-degree is the degree is the number of edges attached to a node. So let me go ahead and draw in a different color so we don't get it nearly confused. So here, we've got this node here. This node has a degree. So there's two types of degrees we care about. There's the out degree, which is the number of outgoing edges, right? So this node has an out degree of 3, and now it has an in degree of 1, where it has one edge going into it. All right, so how does Kahn's algorithm work? Well, for our puzzle, it's pretty simple. What we're going to, in order to figure out what order everything is in the password, we look at all our nodes and find the one that has an in degree of 0. And in degree is a function in Jung, which is super useful. So what we do, so we look at all these and look for the one that doesn't have any arrows pointing into it. And if you notice, there's only one of those numbers. Only 7 doesn't have anything pointing into it. So I'm going to go ahead and delete 7, and I'm going to delete any nodes or edges that were coming out from 7. Just by the way, in Jung, if you delete a node, it deletes all outgoing all the edges attached to it. So super useful there. And I'm just going to write it down as part of our answer. Draw. There we go. It wasn't going off the eraser. There we go. And then we repeat. And because there's going to be a unique solution for this, because of the way this puzzle is designed, you don't have to worry about it breaking any ties here. There's always going to be one possible answer. So we look again. Which node has an outgoing has an in degree of 0? 3 has no incoming edges. So we delete it and all the nodes that were attached to it. So boom. Let's see. I think we missed one possible thing here where let's see. Because we definitely don't have one, because we definitely have 2 nodes here. So 7, So 316, right? So you're going to read this entire file and you're going to be able to get everything. So 316. So we see that 6 has an in degree of 0. I started earlier than I should have, but I didn't want to have to go through this entire file. So now 7. So now 1 has an in degree of 0, so we delete all the nodes coming out of 1. 1 has an in degree of 0, so boom, boom, boom. Okay, and so let's put 6 back there. Okay, so 731, and then we just continue and 6 would be next. And so if we go to our answer, you'll see that I've got 7136, and then it will go on in order. That is so when I'm saying you can do this one on paper, I really mean it, except, this is a coding class, so you got to code it. But so this problem is broken up into basically 2 parts, which is read the file and then, into 2 parts. Read the first part is the file reading, where you read this file and build the graph. The second part is the second part is actually implementing Kahn's algorithm, that part where I was solving. So let's talk about the first part. You're going to be wanting to so the data structure you're going to want to use, as aforementioned, is a graph. Specifically, you want a graph of a graph of integer, right? Because our nodes are integers. A graph of nodes of our vertices being of type integer and our edges being of type, and this one seems a little weird, but I'm going to say string. Why string? Well, because if I want to add so what you're going to do is you're going to read this file, okay, and you're going to read line by line. So what you're going to do is you're going to get your line. So you're inside your loop, you're going to go and read your line, and you're going to be like string line is equal to, scanner dot get next line. So you're going to get your line, right? And then you're going to basically want to go through it and get, the individual characters. So you're going to get to want to split up into your first, the first character, the second character, and the third. What am I doing? Could have just done, right? I could have just written this out like this. First, second, third, great. Just like that, right? So you split it up into your 3 individual characters. Okay, so here's the important, my time-saving tip for you. When you're adding an edge from, let's say, A to B, you say your graph is called graph. The function you'll be using to build this graph is graph.add edge. All right, and what are you going to be doing? And it takes 3 arguments: the edge name, and then your 2 things. So say you've got A and B are your edges. Here's what are your nodes. Here's what you want to put in from your edge. And I just simply know this from long-standing having done this. A plus empty string plus B. So in other words, if we're trying to add at nodes 3 and 1 to the graph, then the edge that's going to connect them is going to be called 30. Is going to be called not 31, but the string 31. Now the reason for this is because any edge that you're adding has to have a unique name. So for instance, you just can't like name them whatever you want, because if you try to add the same, so if you call your edge Bob, and then you try to do this, like 3 and 1, and then we've got Bob, and then we've got 1 and 6, and you also put Bob there, it will crash. Jung will crash you. So, but you're going, wait a second, what about these repeats, right? We've got a, let's see, yeah, 7, 6 over here and a 7, 6 over here. Not to worry, if you give it the same name and it's between the two nodes, it's just going to simply go, oh, that already exists, let's move on. Because, so what it is that you can't have something with the same name at 2 different points, representing the 2 different edges. You can't have the same edge between 2 different pairs of nodes. And it tells the difference between 2 different edges by what the value is. Okay, so that's your first part. Just reading it and just simply parsing the file. That shouldn't be too much difficulty at this point in your studies. The second part is Kahn's algorithm. Okay, which we just simply look, it redirected us to topological sorting, and it brought us down to here, and it said Kahn's algorithm, not to be confused with Kuhn's algorithm. Okay, and it's a bunch of pseudocode, and guess what? Look at these. An empty list with all that will contain, that's your output, L. S, it's a set of all nodes that has an incoming edge. So you're going to need to initialize that by finding the first one, and then while S is not empty, you grab one from it, put it in your output list, and then just simply use the functions that are built into Jung to do the rest of this. It's fairly straightforward to translate. So, but because you're working with a graph, a list, and a set. A lot of what data structures is showing you is that a lot of problems that are difficult can be solved just by moving things from one data structure to another in the appropriate manner. Or by converting data structures, or just simply putting the data into the appropriate data structure. Data structures solve a lot of your problem because a lot of times just solving an issue is a matter of organizing it. 3223, the class after that, which hopefully one day we will offer in Japan. I was hoping to offer it this summer, but that was not approved, one, and second, considering the number of courses I did teach, probably death that I didn't teach it, would have been a bit overworked. But that one is about problem solving with things that, okay, now we have a data structure, but I'm still kind of lost. So, but regardless, that is the last problem for our homework. So, that's what I've got for you. And let me know if you need me to check off anything for you.